This video is a review of thermodynamics for AP Physics 2. Thermodynamics is the study of the relationship between work and energy and conversions between those two things for systems where that's possible, which is typically for things like gases. And some of the things that we talked about in thermodynamics were related to temperature. So to start off, we learned that there is a relationship between temperature and kinetic energy, and that is that these two things are proportional to one another. So the greater the kinetic energy, the greater the temperature. We also learned about a couple of different temperature scales. We primarily measured temperatures in Kelvin, but we can also express temperatures in degrees Celsius. And we learned a couple things about those temperature scales, but one of the things that we learned is that those two temperature scales have the same spacing between the degrees, between the units of the temperature. The size of the degree spacing is the same, but there's an offset of 273.15 degrees or 273.15 Kelvin, depending on how you think of it. So if I wanted to find the temperature in Kelvin, which we do pronounce just Kelvin, not degrees Kelvin, we take the temperature in degrees Celsius, add 273.15, and we have the temperature in Kelvin. Now, one of the important things that we learned is that if temperature is related to kinetic energy, if I start to remove the energy from a gas, then there should be a point at which I can't remove any more energy, a minimum temperature which corresponds to a minimum energy. And that temperature is at negative 273.15 degrees Celsius or 0 Kelvin. And so one of the reasons why we use the Kelvin scale is because it's defined in a more physical way, where the 0 on the Kelvin scale is the theoretical lowest temperature. And one thing that definitely matters is we probably don't need to worry about the 0.15 when we're doing a calculation. Just adding or subtracting 273 to make temperature conversions is probably just fine. One of the laws of thermodynamics that we studied said that if I take two objects that are at different temperatures and they are in contact or near one another, then eventually they will come to be the same temperature. We understand the relationship between temperature and kinetic energy through the kinetic theory of gases. And as I said before, the kinetic energy, or more properly the average kinetic energy of the particles in a gas, is directly related to the temperature. And we made that relationship with the following equation. The average kinetic energy is equal to 3/2 a constant, which is Boltzmann's constant, which is given below, 1.38 times 10 to the negative 23 joules per Kelvin, times the temperature. And so Boltzmann's constant is measured in joules per Kelvin, and so the temperature needs to be measured in Kelvin. And when that happens, if the average speed of these molecules goes up, then we see that the temperature we measure in Kelvin is going to go up. And so this is the relationship between those two quantities. In a gas, however, each gas particle has a different speed. If you take a box of a certain gas and you look at each one of the individual molecules in that box, or each one of the individual atoms in that box, then each one would have a different speed. And for that reason, we have to use average speed. But since in the kinetic energy equation the speed is squared, one of the things that we do is we take the square root of that speed to define a quantity which we call the root mean squared speed, or the root mean squared velocity. And we solve for the square root of that squared average speed. We get the equation that is up here on the right. And that speed is not the average speed, and it's not the speed of an individual particle. It is the speed which is the square root of the average of the squares. And really what that is it's our best measurement of something like the average speed of one of these particles that would be in a gas which could have a wide range of different speeds. And what's important here is that as long as you remember the equation that's in the red box, then you should always be able to solve for the root mean squared velocity, because all we're doing is solving for v in the equation on the left. And one of the things that we find, or a couple of things that we find with this equation, is that first, if the temperature goes up, then the things are moving faster, but that relationship is not a direct relationship. For if the temperature doubles, the speed only goes up by a factor of the square root of 2, and so there's a square root relationship there. But also, if you are talking about two different particles, and some of them are heavier than the other, then their average speed might be less, or their root mean squared speed might be less, and so there's a relationship not only with the temperature but also with the mass of the particles. We also studied gas laws when we studied thermodynamics. And perhaps the most important gas law to remember is the ideal gas law, which relates the pressure, volume, temperature of a gas to the number of moles of the gas and the ideal gas constant. And so I have a list of a lot of those, a lot of the constants that we use in the different gas law equations on the right. R is the ideal gas constant, which is just 8.31 and is measured in joules per mole per Kelvin. If you see a lowercase n, that is the number of moles of the gas. And so if you're told that the gas sample that's being used in a problem has 3 moles or 2 moles, then that would be lowercase n. If you see a capital letter N, that is the number of particles in the gas. And so you should expect that that would be an enormous number, something times 10 to a very big number. And we see that in a different expression for the ideal gas law with the capital letter N, and instead of the ideal gas constant, Boltzmann's constant. And so once again, Boltzmann's constant is 1.38 times 10 to the minus 23. And there is a relationship between the number of moles, the number of particles, and N naught, which is Avogadro's number. And it should make some sense to you, especially if you think back to your chemistry class, if in 1 mole there are 6.02 times 10 to the 23 particles, right? This number here on the right is Avogadro's number. And Avogadro's number is the number of particles that are in a mole of something. It's kind of like counting dozens, right? So I know that there are 12 eggs in a dozen, but there's also 12 cookies in a dozen. It doesn't matter what I'm counting, the number of things in a dozen is always going to be 12. The number of things in a mole is always 6.02 times 10 to the 23 things. And so if lowercase n represents the number of moles, if I have 2 moles of something, the way that I find the total number of particles, which is this capital letter N, would be I would multiply the number of moles by the number of particles in a mole. And so if I only have 1 mole, the number of particles is 6.02 times 10 to the 23. If I have 2 moles, that's 12.04 times 10 to the 23, and so on. And what we did with these ideal gas laws is, first we needed to know that there were 2 ways of expressing that. But also, since n, the number of moles of the gas, is typically constant, and because r is a constant, that means n times r is a constant, which means that the product of P times V divided by T is a constant. And the reason why that's important is because it gives us this relationship where at some initial moment and at some final moment, or in state 1 and state 2 of a gas, P times V divided by T should be the same no matter what. And so I can start to make gas law equations which allow me to relate all 3 or 2 of those variables at a time. And we ended up with at least 3 different gas laws that we could use to solve different types of problems. And so none of those gas laws are given on your equation sheet, but the ideal gas law is. So as long as you remember what's constant in those equations, typically N and R, then you can remember that P times V divided by T is a constant and use it to derive these three gas laws. First, we look at situations where there's a constant temperature. In this case, the pressure and the volume have an inverse relationship. If the pressure goes up, the volume goes down. The way that I got that equation that's on the right-hand side, this one here, which says P1V1 equals P2V2, is I took my equation that's underlined in yellow on the left, and I crossed off the thing that's constant. If it's constant, it won't play a role in the equation. So I crossed off the temperatures, and I got the P times V equals P times V. And the same thing goes for the next couple of equations, where the volume is constant, the temperature and pressure point in the same direction. They have the same, they are directly related. And so I got that by crossing off the V in the equation, and similarly I got the last equation by crossing off the P's, because the P was constant. A graph of pressure versus volume, where the temperature is constant, should be a inverse relationship, and we should get linear relationships between the pressure and temperature or volume and temperature. So make sure you know how to start with the ideal gas law and derive each of these equations, but also make sure you're comfortable with each of the constants that can be used there, so that way, regardless of the information that's given to you, you're comfortable in solving the problem. Another topic we studied was the first law of thermodynamics. The first law of thermodynamics relates the internal energy, the thermal energy, and the work of a gas to one another. And so when thermal energy, which is represented by the letter Q, is transferred into a system, the internal energy, represented by U, increases, or the system does work. And so what that means is, if I have a system, maybe I have a gas that's enclosed in a piston, and I am transferring thermal energy into that piston, either the internal energy of the gas is going to increase, which is associated with an increase in temperature, or as I'm adding thermal energy to that gas, it's going to do work. And one way that a gas can do work is maybe it pushes up on the piston and its volume changes. And so either one of those things, or maybe both of those things, are possible. One of the things that we know for sure is that the work that a gas can do has to be associated with a change in volume. And so we can calculate work in cases where the volume changes. And one way that that happened graphically is sometimes maybe in cases where there's a constant pressure, but the volume is changing due to heat being added or something like that. Then we might get a graph that looks like this, and the area under that red line would look like this. The height of that red box would be a pressure, and the width of that red box would be a volume. And so the area of that red box would be P times V, or you could think of it as P times delta V. And so the area under the curve of a pressure volume graph is the work done on the object. And so that's pretty important. We need to make sure that we know anytime there is an area under a curve or a line or some shape that's being drawn in a pressure volume diagram, we should be able to calculate the work underneath that curve. In order to better understand the relationship between U, Q, and W, the internal energy, the heat, and the work, we've got this table here because one of the, with all the calculations with this law of thermodynamics, you need to make sure that you have the right sign, either positive or negative, for each quantity. So first off, if delta U, or U, the internal energy, is positive, then that means the temperature has increased. Or if the temperature is increasing, then you know that delta U should have a positive value. And similarly, if delta U is negative, then you know the temperature is decreased. And I guess with those two things together, if delta U is 0, then that means the temperature is not changing. And so if there's ever a case where you're asked to apply the first law of thermodynamics and you know that the temperature is not changing, then you know delta U is equal to 0. For Q, if heat is entering the system, then Q is defined as being positive. And so we need to remember that for most problems where we're thinking about the first law of thermodynamics, we're going to be talking about a system and the surroundings. And so if heat is entering the system from the surroundings, Q will be positive. And if heat leaves the system, then Q will be negative. Or similarly, if heat is going from the system to the surroundings or the environment, then Q should be negative. And maybe that makes some sense because what we're really talking about is the gas. We don't really care so much about the environment. And so if heat is entering the system, the heat transfer should be positive because there's a positive amount of heat going to the gas. And if it's leaving, then it's going to the environment, and so that makes Q negative. There's a similar definition for how work is done. If work is done on the system, so the environment or you or somebody's pushing down on a piston maybe to compress the gas, work is being done on the gas, it's being compressed, then work is defined as being positive because that would work to increase the internal energy of the gas. And if work is being done by the system, so typically expansion, so maybe I'm adding heat to a gas and it's expanding by pushing up on the piston, then work is defined as being negative. So typically when the volume is increasing, the work is negative, and when the volume is decreasing, the work is positive. And maybe you remember some of the difficulties we've had with trying to talk about and use words like on or by to describe what's happening with the work. But in general, you should be able to remember the convention that if the volume is increasing, the work is very much going to be negative. With this idea of looking at PV diagrams and thinking about how properties of gases change as they move from one state to another, we studied several different thermodynamic processes by looking at PV diagrams. So the first process that I have here is an isothermal process, a process where the temperature is constant. And if you think back to a couple of slides ago, for the gas law where the temperature was constant, we saw that there was an inverse relationship between the pressure and the volume. And that's given here by this graph. So anytime you see a curve that looks something like this, you should be thinking, is this a case where the temperature is constant? If the temperature is constant, that means the change in temperature is 0. And earlier I stated that if the temperature is not changing, the internal energy is not changing. And so if you think back to the first law of thermodynamics, if delta U is 0, that means however much heat is being transferred must be equal and opposite to the work that's being done. And although it might be kind of tricky, we should be able to calculate the work underneath this curve. Or at least we need to know that work is being done because there's an area underneath that curve. The volume is changing, so work is being done. The next process is an isovolumetric or isochoric, and I think isochoric is probably more popular than isovolumetric, is a constant volume process, in which case we go from one pressure to another without changing volume. In this case, the volume is constant, which means that there's no work being done. And that's pretty evident because there's no area under this curve. It's just a vertical line, so there's no area underneath that. And in that case, if the work is 0, then by the first law of thermodynamics, any change in the internal energy is directly related to the heat transfer, Q. Next we have an isobaric process. An isobaric process is one where the the pressure is constant. And if the pressure is constant, the graph should look something like this, right? It has to be a horizontal line where the pressure is the same everywhere. And therefore, the change in pressure is equal to 0. There's no change in the pressure. Therefore, we should be able to quite easily calculate the area underneath this curve, which would be just a square or a rectangle, in order to find out how much work was done. And so, although nothing is necessarily 0 in this case, by the first law of thermodynamics, we should be able to find the change in the internal energy by knowing something about the heat transfer Q, and then applying the area under the curve, or the equation for work, in order to get the second term in the equation. The last process that we have observed on a PV diagram is an adiabatic process. And an adiabatic process looks a little bit like an isothermal process, because it's kind of got this curve to it like that. But an adiabatic process would be represented in a PV diagram as being more steep than an isothermal process. And actually, if I were to draw isotherms on this, it might look something like this, where the point that I start at might be attached to one isotherm, and the point that I end at might be attached to a different isotherm. And that's quite poorly drawn in that graph because I didn't have a lot of space. But in general, an adiabatic process starts off at one temperature and ends up at another temperature. It is a line that connects two different isotherms, two different temperatures represented by those curves. But it goes from one state to another without any heat transfer. An adiabatic process is defined as not having any heat transfer, and so for that reason Q is equal to 0, which means that any change in the internal energy of the gas is not due to heat transfer, but it's due to work being done. And sometimes this happens in engines where there's very quick compression or expansion of a gas, very quick changes in volume that don't allow any time for temperature or heat to be exchanged with the environment. And so it's steeper than an isotherm, and all the change in internal energy is due to work. There's no heat transfer, so Q is equal to 0. I have down here a couple more bullet points that I want to make sure that we know about different thermodynamic processes. So I talked about the names of each one of these types of processes, but we also need to know, in general, we could talk about the lines in each one of these graphs as being isotherms, isocores, isobars, adiabats. And so for the isobaric process above, that horizontal line that I drew, we could call that an isobar. Or the line that I drew for the adiabatic process, we could call that line an adiabat. And that might be useful if you're asked to describe what's going on in a graph. Also, on the right-hand side, I have drawn a full thermodynamic process where in this there might be an isobaric process, an isochoric process, and an isothermal process, and those three different steps in this cycle are all connected. And so I can go from state 1 to state 2 to state 3 and then back to state 1 by going through a series of steps. And in that full cycle, if I return back to state 1, the change in the internal energy will be equal to 0, because there's a certain amount of internal energy associated with point 1, point 2, and point 3. Also, and just to remind you about a convention with work, we said previously that if the volume goes up due to expansion, that means that the work is negative. But if you look at the equation, in the equation, delta V is Vf minus Vi, so the only way that we can make it negative is if there's a negative sign placed out in front of the pressure. And so for that reason, if you look on your equation sheet, or just by convention, there's a negative sign that's placed there in order to match the sign convention that we've selected. Next, I'd like to talk just a little bit about heat transfer. First, we learned that heat can be transferred in a couple of different ways: by conduction, by convection, and by radiation. So a quick example, maybe something you should have in your head just to remember all three of those, is that conduction has to do with touching. And so if two things are in contact, if they're touching, then it's possible for heat to be transferred by conduction. So for example, maybe the handle on this pot, which is boiling the water, is connected to the pan, and so if the pan gets hot, maybe it's possible for the handle of the pan to get hot. Or the water that's in this pan is in contact with the bottom of the pan, and the bottom of the pan is what gets hot, and because the pan is getting hot and it's touching the water, then by conduction it's able to transfer some of that heat to the water. Convection typically is thought of as happening with fluids, so things that can flow, where as the water heats up, some of the water at the bottom will get hotter and become less dense, and then it will go to the top, and some of the cooler water will fall down, and so we'll get convection currents flowing in the water, and that contributes to the heating. This happens in your home as well. When hot air is pumped into your home, there's convection currents that flow if you have forced air in your home, where some of the cycling there allows heat to be transferred to different parts of a room. And then lastly, radiation has to do with the radiation of energy away from objects through space. And so if you get anywhere near this hot pan or this hot fire, then you can put your hands nearby and feel the heat coming off of the fire or maybe the pan. And so for conduction, the things have to be touching. For convection, it typically happens with fluids and the movement of a fluid. And with radiation, heat can be transferred through the air even. And for one of those types of heat transfer, conduction, we learned a little bit more about that. And we learned about the rate at which heat flows across a material, so say a conductor, where that conductor has a certain length and a certain cross-sectional area. And maybe if I have like a bar or a chunk of this material, the left side and the right side of that material maybe are at different temperatures. And so the temperature difference, right, the temperature difference across that material, along with the length and area of it, if I know those things, then I can begin to think about how quickly the heat is going to be transferred. The only other thing that I'm missing is this letter K here, which is a representation of the thermal conductivity of the material. And the way that we summarize all of this in equation form is with this equation here. So each of those variables plays a role in the rate of the transfer of heat across a material. And maybe you notice that as the length increases, the rate of heat flow would decrease. As the temperature difference increases, so if I have the left end and the right end of a piece of a material at vastly different temperatures, that actually contributes to a greater flow of heat. And then obviously something that we really need to know is that if something has a higher thermal conductivity, then it's going to be doing a much better job of transferring heat across it. And so if I have 5 different metals and I keep the ends of each of the rods at the same temperatures in some creative way, then the ones with higher thermal conductivity will transfer the heat across them more quickly. One of the things that conceptually was kind of tricky for us was the second law of thermodynamics, which states something like the fact that a natural process, something that happens naturally, always flows from a state of order to a state of disorder. And the phrase natural process is important because it's very easy for us to do something in which we go from a state of disorder to a state of order. I can clean my room, I can make a sand castle, any of these things. But those are not natural processes. So when I build a sandcastle, it requires some energy for me to do that. When I clean my apartment, it requires me some energy in order to accomplish those tasks. And I lose more energy than I gain, or I've created more disorder in the fact that I've had to consume a bunch of energy and I'm radiating energy into the environment as I'm walking around cleaning my apartment, or I'm radiating more energy and using more energy to build my sandcastle than I am building order in the sandcastle, if that makes any sense. And so for natural processes, things that happen naturally, they always flow from a state of order to a state of disorder. And it's just more favorable for processes like that to happen, and so they happen. And so the example I have here is I have a box that maybe is initially separated, and then I remove a divider between those two gases. One of the gases is at 300 Kelvin, and the other is at 400 Kelvin. And maybe the gas on the left and the gas on the right, they aren't even made of the same types of particles. If I remove that divider and then give them some time to bounce around, then we come back later, and not only would they come to equal temperatures, but the gas particles would also be mixed. And that's just because it's statistically likely that they mix, and it's statistically likely that the molecules that have a higher speed, so it's not just entirely random, the molecules that have a higher speed are going to be moving faster. And if those are moving faster, then they're more likely to collide with other particles. Okay? And if they're more likely to collide with other particles, then that means there's more likelihood that they will lose some energy to those particles in those collisions. And then in doing so, they're transferring some of their own energy to the lower energy particles. And so in general, in this box, the speed of the particles in the box on the right at the higher temperature is greater, and then on the left where the temperature is lower, the speed is going to be less. And on average, those blue particles are going to be colliding more and transferring more of their energy to the red ones. Are there cases where a red particle might give some of its energy to a blue one, or a blue one might give it to another blue one? Yes, but over time, because there's lots and lots of particles, it's much more likely that they'll come to thermal equilibrium, and they will have reached a state where there's not so much order, right? We've gone from two separated sets of particles to a much more disordered state where everything kind of has the same temperature and they're all mixed up. Lastly, a graph that we've definitely seen a number of times that I want to point out here. Here I'm plotting the number of molecules, or the number of atoms, or whatever, versus the speed. And the red line and the blue line represent a gas at two different temperatures. And you can see that there's definitely a peak, and those peaks correspond to a particular speed. I said before that gases have a wide range of speeds, but we still say that gases are at a particular temperature. And so most of the particles have a speed that's given where those green lines are, but some of them are faster, some of them are slower. And we call this distribution a Maxwell-Boltzmann distribution, which shows that range of speeds. Since molecules can't have a speed less than 0, if I start to cool the gas down, the molecules all start to move more slowly. And so you should imagine that peak shifting to the left, right? Over here on the right side of the graph, these are big speeds. And on the left side of the graph, those are small speeds. So as I move from right to left, the temperature is going down. And so yes, the red peak is higher than the blue peak, but its temperature is less. And the reason why this occurs is because gas molecules cannot have a speed less than 0, and so the distribution can't go beyond this location right here. It cannot go beyond this axis, right? Because you can't have a speed less than 0. And for that reason, as the gas cools, more and more molecules are stacking up at the lower speeds. So the distribution is forming a more narrow peak and building up a higher peak that is going to be near 0 but not quite 0. And definitely the molecules can't go anywhere else. So higher temperature gases have peaks that are further to the right and they're more spread out. And lower temperature gases have peaks that are further to the left and higher.